Hello, Algebra 2. We're going to be working on Edgenuity section 9.1 called Linear Programming. We've got two objectives. We want to maximize a function given constraints and represent and solve real-world problems using linear programming. So we'll be talking about what that all means as we go through this. Let's talk about a typical type of problem. Let's say we're producing bottled drinks, coffee bottled drinks, something that's going to go up in the grocery store for people to buy, okay? And we're going to make two types. We're going to make cappuccinos and cafe au lait. The cappuccinos require 6 ounces of coffee, 2 ounces of milk, and they give us a 40-cent profit. The cafes au lait need 40 ounces of coffee and 44 ounces of coffee and 4 ounces of milk, and they give us a 50-cent profit. Every day, we have in our factory, in our facility where we make these, we have 720 ounces of coffee and 400 ounces of milk. That's every day we make sure we have that much. Okay? Now, every day, we want to make at least 80 total drinks. We want to bottle 80 drinks. Okay? Let's just, for the sake of being uniform, let's let X be the bottles of cappuccino that we're making and Y be the cafe au lait. So then we got to talk about what are the constraint equations and what is the objective equation. The constraint equations are the equations that are going to make up a graph, a so-called feasible region, that is going to allow us to see the vertices, and the vertices are what become important here. And then the objective equation is the one that we are going to optimize, either maximize or minimize, depending on what makes the most sense for this particular problem, right? So in this case, the objective would be to maximize profit, right? So usually I have found that doing the objective equation first is more helpful, because then you know what you're going to maximize and you know not to include that. And how do you know where to look for the objective equation? Well, the objective equation is the one that you always want to maximize or minimize, or optimize, you might say. And we're looking to optimize profit, right? So we want our objective equation to be our profit equation. What is profit? Well, we make 40 cents for every cappuccino, so that's 40 cents times the number of cappuccinos, and plus we make 50 cents for every cafe au lait that we sell. So our total profit would be 40 cents times every cappuccino plus 50 cents times every cafe au lait. So that's our profit, and that's our so-called objective equation. Now let's worry about the constraint equations. The constraint equations are the ones that are going to help us figure out where our vertices are, and we're going to talk more about that as we go. But so notice we have a way of making cappuccinos. So let's talk about how much coffee we will need. Okay? Every cappuccino needs 6 ounces of coffee. Every cafe au lait needs 4 ounces of coffee. So 6 ounces times the number of cappuccinos plus 4 ounces times the number of cafes au lait And then how much total coffee do we have? We have 720 ounces of coffee in total. Now, we don't necessarily need to use all of that coffee, but if I were looking at it on a number line, let me show you this technique. It works really well for this. And then think about like some number before that and some number after that. If you think about, okay, here's the most at 720 ounces, right? And then you ask yourself, could I have this? Could I have this? Okay? Could I have 700? Could I use, let's say, could I use 700 ounces of coffee? Well, sure. Why not, right? I have that amount. Could I use 740 ounces of coffee? No, I don't have that. So when you start putting that all together, you can see that you could use 720 ounces, or you could go backwards. And this gives you a really good way to create your inequality, because I could be equal to 720, or I could be less than. And the less than and greater than symbols are just the ends of arrows pointing on a number line, right? So less than, and then half of an equal sign for or equals 720 ounces. So that's how you can check that idea and make sure that you're getting the correct inequality. You don't necessarily need to, but it can be helpful. Okay? So that's the coffee. Then, of course, we have the milk that we're going to use. So let's talk about how much milk we're going to use. We need 2 ounces of milk for every cappuccino, so 2 ounces of milk times every cappuccino, plus 4 ounces of milk for every café au lait, so 4 times every café au lait. And we've got 400 ounces of milk, so if you think about that, I'll draw the number line again. 400 is our target. We could definitely use 400. Could we use 410? No. Could we use 390? Sure, why not? So then we're going that way. So it's a less than or equal to option again. So less than or equal to that maximum 400 ounces of milk. And then what's the last thing? Well, the last thing is, how many are we going to make? We got to produce at least 80 drinks a day. So that's our total amount. Our total amount is the amount of cappuccinos we make plus the amount of cafés au lait that we make. And one more time with the number line, could we make 80 of them? Absolutely. Could we make 70 of them? Sure. No, we can't. At least 80. So no, we can't make 70. Could we make 90 of them? Absolutely. Okay? So that means that we're going in this direction now. So now we're talking greater than or equal to 80. And those are our constraint functions. Take a look at that for a moment. And let's move on. All right, so now we've got these equations, and we're going to add 2 here. We can't create negative numbers of cappuccinos or cafés au lait, so each of those has to be at least 0, right? And we want to graph these constraints, and we'll shade the feasible region. I'll talk about why that's important as we're doing it, okay? So when you've got problems like given to you like this, the easiest way to graph them is to get their intercepts. So if I'm doing x plus y is greater than or equal to 80, if I do the x-intercept, that means here's the way to do intercepts, or the way to think about them so that they're easy to do, okay? To get the x-intercept, you think that that is the x value when the other one equals 0. Okay? So the x-intercept is the x value when y equals 0. If you word it that way to yourself, then it becomes much easier to figure out which one's supposed to be 0 and all that. If you just try and I never am able to just straight remember it. It just never works for me. Okay? So if I do that, then I'll be looking for x. My y will be 0. Oh, and then we want to replace the inequality with just an equals. Okay? And that'll be x equals 80. So one really good point for this one is an x value of 80, a y value of 0. Okay? And then I could do the same thing with the y-intercept, and you'll see that it works in exactly the same way. The y-intercept is the y value when the other one, x, equals 0. So we have 0 plus y equals 80, which just means that y equals 80. So we have another good point of 0 and 80. So let's do some things here so that our constraints are kind of easy to see which one we're graphing when, okay? This would be constraint A, this would be B, this would be C, this would be D, and this will be E. And that's just going to help us keep organized more than anything else. And I'm going to keep getting intercepts for each one of these, and we're going to keep figuring these out, and then we'll graph the whole thing. All right? So for part B, for inequality B, constraint B, whatever you want to call it, let's do that again. I've got 6x plus 4y is less than or equal to 720. Let's get the x-intercept. That'll be the x value when y equals 0, and we'll use an equals instead. We can ignore that, and we'll have 6x equals 720. We can ignore that because 4 times 0 is 0, and so we've got 6x plus 0, right? Then we divide by 6 on both sides, and that'll get us x equals 120. I do believe, yeah. So one of our points is an x value of 120, a y value of 0. That is our x-intercept. And then Our y-intercept will be the y value when the other one, x, is equal to 0. So this is then 6 times 0 plus 4y equals 720. I can do 6 times 0 is 0, and then add 4y is just 4y equals 720. Divide by 4, divide by 4. 4 over 4 is 1. 1 times y is y. Equals, and then 720 divided by 4. Let me do some side work here. That would be 1, bring down the 4, subtract, get 3, bring down the 32. 32 divided by 4 is exactly 8, so 180. Okay. So 180. So our y-intercept is an x value of 0, a y value of 180, and that's B. Let's work on C. Be the last sort of difficult one to do. 2x plus 4y less than or equal to 400, and then we'll get the x-intercept. That's the x value when the other one equals 0, and we'll set it equal to 400 and solve. 4 times 0 is 0, so 2x plus 0 is 2x equals 400. Divide by 2, divide by 2, and x equals 200. So our x-intercept is an x value of 200, a y value of 0. And then let's get our y-intercept. Get rid of this. And our y-intercept will be our y value when the other one, x, is 0. So it's 2 times 0 plus 4y equals 400. And then 2 times 0 is 0. So I can ignore that and have 4y equals 400. I'm not really ignoring it. It's becoming 0, and I'm adding it to the other thing, and 0 plus anything is itself. That's what I'm really doing there. So divide by 4 on both sides, and y equals 100. So then our y-intercept is an x value of 0, a y value of 100. And so I have 2 good points for each of those 3, and then these ones, this is just a vertical line at x equals 0 and a horizontal line at y equals 0, which are just the 2 axes, right? So it looks like this. First, x equals 0 is there. Y equals 0 is there. And then x has to be greater than 0, so that's going to be all the stuff over here. Y has to be greater than 0, so it's going to be all the stuff here. So we're only talking about this area, this quadrant right there. Okay, so that'll be important. We need, let's put some markers up. A max x value, or a max y value of 180. A max x value of 200. And I know that's not quite to scale, but I'm squeezing it in here, so bear with me. We need value, we need a y value at about 100. We need another one at about 80. We need an x value at about 80. We need another one at about 120. And you can always do this with graphing. As long as you label it, you're good. Okay? And then, so 80, 0 is there. And 0, 80 is there. And this is how we will graph A. And remember, we don't have to go beyond this area right here. So I'm only going to connect it from there to there because I'm already constrained. If I were to go like out to here, I'm not even going to be worrying about that anyways, so I'm just not going to worry about it. Now, notice that this is greater than or equal to. One of the things that you have to do to know how to shade it is you have to solve it for y. Okay? So x plus y is greater than or equal to 80, and then I would subtract x on both sides, and traditionally you'd write y is greater than or equal to negative x plus 80 to give you an idea. And then your, like that, that is your greater than. So your shading would go start at the line and shade up. Okay? So that's how I know that this one will shade up. And I'm just going to make a little note there. Okay? So A, and this is A, will shade up. Okay? B, we have 120 and 0. We have 0 and 180, and again, I can just connect those two. And this one looks like it's less than, but it's good to check. This is B. I'll label it in a second. And so we've got 6x plus 4y is less than or equal to 720. The reason you need to do this is because from time to time in the solving for y work, you wind up needing to flip that inequality, and then that changes how it shades. So let's solve it for y. We'll have to subtract 6x on both sides. That's not going to change anything. So 4y is less than or equal to, traditionally you'd put negative 6x plus 720, because you want the x part out in the front there. And then divide by 4, and I'm just going to divide the whole thing by 4 because all I'm really concerned with is, does this change the shading? And it does not, because I'm dividing by a positive number. You only flip the inequality if you multiply or divide by a negative number. So this is still less than or equal to negative 6x plus 720, all of that over 4. There is some more simplification to do, but I'm not concerned with it. I'm only concerned with the fact that I'll be shading down. Okay? So there's that work. And so I'll be shading down. That is, I'll start at the line and I will shade down. And notice that now we're getting like a corridor, right? We've got like a tunnel. So there's equation B. Now C, we've got 200 and 0 is one of our points. That's way the heck over here. And 0, 180 again here. So then we're gonna do that. And this is less than, so you would think we'd shade down, but we got to be sure, right? So for C, 2x plus 4y is less than or equal to 400. And let's subtract 2x on both sides, and that'll be traditionally written 4y is less than or equal to negative 2x plus 400, so that the x part is out front there. And then divide the whole thing by 4, divide the whole thing by 4, and none of that is going to change the direction of the inequality, so this one will continue to shade down because of the less than. Okay. And we've already determined for these how that changes things. So for A, we shade up. For B, and this is C here. For B, we shade down. And for C, we shade down. And where is our feasible region? What is our feasible region? Well, our feasible region is our region where all the shading comes together. If they were, if we were using a different color for each one, and we had 3 colors, the shaded region that we would worry about would be the new color that we create by combining all 3 colors. Okay, actually all 5 colors, because we're also worried about being in that quadrant, in this quadrant here, right? So maybe I'll show that. Let's say we put all the colors together and we got green. I know that doesn't really work, but all the colors come together in this little corridor here. And so this is our so-called feasible region, right there. So then the next part of this, and I'll talk about it, is to say, okay, where are the vertices? So the vertices are at, there's one at 0, 180, right there. There's one at 0, 80, right there. There's one at 120, 0, right there. And there's one at 80 and 0, right there. Okay? And the reason that these vertices are so important is because that is how you are going to do what we call optimize this problem. Remember, we were concerned with our profit here. And so what we're going to worry about and it's just a property of these types of problems. This is how these problems work. There's exceptionally long proof for it, but it is true that the vertices are where you maximize and minimize that profit equation. And so what you would do, and we'll do this in a later problem, is you would put the x and y from each of these into this profit equation here, and one of those four will give you the most profit, which just by glancing at it, you should see that it's the first one. And that tells you how much of each thing you should be making. So, like, that one's the profit one, right? That produces the most profit because you're making 50 cents for each Y for each cafe au lait. So, in theory, based on what we're given here, for your business, you shouldn't be making any cappuccinos. You should only be making cafe au laits, and you should be making 180 of them a day. That might seem a little counterintuitive, because you might think, oh, well, but people are going to want to buy cappuccinos also. But that's, given the constraints that we were given in this problem, which is to say, we don't necessarily care if we make any of one of them, then this is what we come out with. All right, I'll give you a moment to look at that. And let's move on to our next problem. So now, let's talk about this maximizing, minimizing, what we call optimizing part of this. Okay? If I tell you that the vertices of a feasible region are these points right here, and I ask you to find the maximum and minimum for an objective equation, which I give you right there, what you have to do is you have to test each one of these and see which one comes up with the most, right? And there are some things you can do to narrow this down, right? For example, I see the 8 here, and so between these two, certainly this one will be bigger than this one. And between these two, certainly that one will be smaller than that one. So I'm going to take that 0, 100, and I'm just going to eliminate it as a choice for either optimization. It cannot be the maximum, because this one's going to come out bigger. It cannot be the minimum, because that one's going to come out smaller, right? And look at these two. Certainly, this one will come out smaller than this one, because if I'm multiplying by 80 here, instead of multiplying by 80 there, it's going to be bigger. And then between these two, certainly this one's going to come out bigger, so I can also throw out 80 0, because it can't be the smallest, because that one's got to be smaller, and it can't be the biggest, because that one's got to be bigger. So there's two that I have been able to throw out completely, okay? So now I got to think about the other ones, right? For the maximum, for example, for the maximum, I shouldn't bother testing that one, because certainly that one's got to be bigger. I've already eliminated 2 that I don't have to worry about at all. So I'm going to, when I think about 0.80, it certainly can't be the maximum. So I'm going to throw it out for the maximum only. It could very well be the minimum, right? And then I'm left to only test 2. And that's what you got to do. Narrow them down and then test what you have to test. So I have to test 80, 60, and I have to test 120, 0, right? So, and what I do is, here's the X, here's the Y, here's the X, here's the Y, and so when I test 80, 60, I'll say F equals 8 times 80 plus 5 times 60, and I'll just do the arithmetic and get an answer. Okay, 8 times 80 is 8 times 8 with a 0 on the end, so it's 64, add a 0, so 640. 5 times 6 is 30, add a 0 on the end, so that's 300. So I get a total of 940 for that one. And then let me test the 120 and 0. That'll actually be even easier to calculate. 8 times 120 plus 5 times 0. 8 times 12 is 80. Plus 16 is 96, so this is 960. It's 96 with 0 on the end. Plus 0 is 960. So there's the maximum. Now for the minimum, I can certainly throw out the maximum. And the other 2 that I can throw out immediately, so all I have to test is 0.80 and 80, 60 to see which one's smaller. And I've already done 80, 60, so 80, 60, I shouldn't have to do that again. It's 940. And then I just need to do 0.80. That equals, let's see here, 8 times 0, that'll be nice. 5 times 80, that'll be really easy. Equals 0 plus 5 times 80. 5 times 8 is 40, with a 0 on the end is 400. So 0 plus 400 is 400. So the minimum is 0.80. And there we have it. So we have maximum and minimum there. I'll give you a chance to look at that for a moment. This is how we optimize. All right, let's look at our next problem. Let's say we own a printing company, and we're going to order some supplies, the same types of supplies, let's say paper. It's a printing company, right? We're going to order paper, the same type of paper, from suppliers X and Y. Supplier X charges us $25 a case. Supplier Y charges us $20 a case. Okay? And maybe there's a difference in the paper quality. We don't know. But we definitely know that we need 45 cases of paper altogether. And we've determined that we're not going to order, we can only order up to 30 cases from supplier X. Maybe they have better paper, but they charge more. So we say, yeah, we definitely want to order from them because some of our customers like the nicer paper a little bit more, but we're never ordering more than 30 cases from them, say, per day or per week or whatever we're talking. Okay? And we need, I hate the way that they word this, but this is how the problem words it, so I'm wording it this way to stay consistent. We need no more than 2 times as many cases from supplier Y as we do from supplier X. So however much we're going to order from X, we're going to order no more than twice as much from supplier Y, okay? So if we order the 30 cases from supplier X, the most that we're going to order from supplier Y is 60 cases, no more than twice as much, no more than 2 times as many cases, okay? Then we want to write the constraints and objective equations. So let's start with the objective equation, because the objective equation is usually the one that you can figure out by asking, what am I going to optimize? Okay? And in this case, we're talking price, right? And what we're talking is, I would want to minimize how much I spend, right? My cost. So the objective equation would be that I want to minimize cost. And what is my cost? Well, it's $25 times every case of supplier X from supplier X that I order, plus $20 times every case that I order from supplier Y. And I would want to minimize that cost. So that's my objective equation. My constraint equations, or just my constraints, you might say, have to do with everything else, okay? So we need 45 cases. You might even interpret that as we need exactly 45 cases, but usually when you say we need 45 cases, what you really mean is we need at least 45 cases, right? So number of cases from supplier X plus number of cases from supplier Y has to be at least 45, and then you can consider a number line and say, well, could I order 45 cases? Yes, absolutely. Could I order 50 cases? I want at least 45 cases, so yeah, sure, I could order 50 cases. Could I order 40 cases? Well, I want at least 45 cases, so no. So it has to go like that, which means we're talking greater than or equal to. The or equal to coming from the fact that I can order exactly 45 cases, the greater than coming from the fact that I can order more than that, and so I'm moving in that direction on the number line. So there's one of our constraints. What else do we have? We can only order 30 cases. That is to say, the most we can order from supplier X is 30 cases, right? So supplier X has some sort of limitation of 30 cases. Let's explore what that limitation is. Can I order 30 cases? Yes. The wording allows me to order 30 cases. Could I order 35 cases? No. I can only order up to 30 cases. Could I order 25 cases? Well, sure, why not, right? I could order less. I can only order up to 30 cases. Now, I know it doesn't quite say that in the wording of the problem, but this is where the interpretation and understanding these ideas unfortunately has to come into play because people don't always say exactly what they mean. So we can have the 30 cases, and we can go back this way. So that's less than or equal to, right? Okay. Now, here's the real crazy part. We need no more than 2 times as many cases from y as from x. So what is our y constraint? Well, it's 2 times our x's. So let's say that we order 30 cases from x. That would be 60 cases from y, right? Could we order 50? Could we order 70? Okay? It says no more than twice as much. So if I order 30 cases from x, I can order 60? Sure, that's no more than twice as much. Could I order 70? No. Could I only order 50? Yeah, sure, that's no more than twice as much. That is, I'm allowed to order a little bit less, but I'm not allowed to order more than that. So that's less than or equal to. So there's that one. And then let's throw in here also that we can't order less than 0 of them. That is, we can't order negative amounts. So the x and y both have to be greater than or equal to 0. Okay? So those are our constraints. I'll give you a moment to look at that. And let's go on to really what amounts to the next part of this problem. This is the same problem. You'll notice we have our optimization equation, our objective equation, and we have our constraints. We haven't bothered with the zeros, but we should keep them in mind, right? So graph and shade the feasible region. So here's our feasible region. Our first part is that we want to be stuck between these two, right? We want to be only in this area because that would be x greater than or equal to 0, y greater than or equal to 0. And then we want to graph each one of these. We might label them A, B, C, and D. So A, y less than or equal to 2x. We can make an easy little table for that. If I make x 0, then y is 0. If I make x, let's make x 30 because it comes up right there. Then y would be 30 times 2, or 60. So that gives me some stuff there. So I've got 0, 0 to graph, and I've got 30, 60 to graph. And then let's have equation B is just going to be x less than or equal to 30. So I'll just draw the line x equals 30, which would be a vertical line, and I'll shade left of that. I'll shade less than that. And then C is x plus y is greater than or equal to 45. We could do x-intercepts here, and y-intercept here. If we do x-intercept, we're looking for the x value when the other one is equal to 0, and we'll change it to equals, and that'll be x equals 45. So one of our points will be 45 and 0. And then we could do our y-intercept. That's our y value when the other one equals 0. So that would be 0 plus y. Wow. Why do I keep writing 40? So that'd be y equals 45, which would give us 0 and 45. So there's our two intercept points, which will make it easy to graph that. And then remember that we have to know how this shades, so I have to solve it for y to really know that, okay? So if I start with x plus y, oh, by the way, I know that a shades down because it's already solved for y, and it's less than. B is a vertical line, so it actually shades left, okay? And then C, x plus y is greater than or equal to 45. I'll subtract x on both sides. And that'll give me y is greater than or equal to negative x plus 45. So it will still shade down. Okay. So now I have everything I need to know how to put all this together. And so I will do 0, 0 there at the origin, and 30, 60, let's see, I got to go up to 45 and over to 45, I know that. So 30 would be like, I don't know, there somewhere. Oh, no, and oops, I messed that up. Let's back up a moment. I have to go to a maximum of 60. So let's make both of those 60. Fix that. So we get a biggest number of 60, right? And then, so I'm going to need a 30. And I'll mark 30 here because halfway is going to be 45. That's also gives me a really good way to identify approximately where 45 is. So, so let's see. We've got 0, 0, and 30, 60. So 30, 60 is like there. So there's that, and I'll extend it further just in case it's needed. Notice that's all in that first quadrant, so it may go on forever, right? And then x equals 30 line is actually going to hit that 30, 60. That may go up forever. And then 45, 0 is there, and 0, 45 is right there, and that would cross like that. Okay, so we've got A here, B here, and C here. And A shades down. Like so. B shades left. Like so. And C shades down. Like so. And our triple shaded area, I'll do in purple this time, is this area right here. And we know two of our vertices. So if we needed the vertices, we still don't know that one right there. But what we do know is that that spot right there is the intersection of A and C. And so what you would do is you would say, okay, let's have y equals 2x and x plus y equals 45, and you would set this up as a system of equations, and you would solve that system, and the answer would give you the intersection. I'm not going to do that now, but that's what you would need to do to get that final point. I'll give you a moment to look at that. And let's go on to our final problem. And here we're given a bunch of constraints, and all we want to do is graph this feasible region, find the shaded area, and find the vertices for it. So the vertices, again, the vertices are really important to this because those are the points to test for optimization. Okay? So let's look at all these. Let's label them first. We'll do A, B, C, D, and E. It's an awful C. There we go. That's a little better. And let's start figuring out how we would do this. Y is greater than or equal to 2x. Well, that one's pretty straightforward. If you want to graph y equals 2x, this would be A here. You could just make a tiny table, 0, 0, and what are some biggest numbers that we're looking at? 14, so let me do 20, and 20 times 2 is 40. So that kind of gives me a good spot. So 0, 0, and 20, 40. So for A, 0, 0, and 20, 40. For B, B is going to be done by intercepts. And A will shade up. So I'll put a little arrow there to remind me of that. Intercepts for x plus y is less than or equal to 14. We'll worry about equals 14 because we're worried about getting points here. The x-intercept would be the x value when y is 0, and if y is 0, you should see that x would equal 14. And if x was 0, that is the y-intercept. The y value when x is 0 would be 14. I've worked that out a couple of times already, so I'll let you guys work it out if you need to. If you solve B for y, you'll see that it still will shade down. So let's put a down arrow there. For C, y equals 1 is what we're interested in, and that's a horizontal line at y equals 1. If you need to see that, you could say, okay, if x was 0, y would be 1. If x was 14, we keep getting 14 in there, then y would still be 1, because there's no x, so it doesn't matter how x changes, right? Y is 1. And this one is y is greater than or equal to 1, so C shades up. For D, there's a little more work to be done, right? 5x plus y, let's call it equals 14. And what I'm going to do here is I'm going to solve it. Well, yeah, let's, instead of equals to start with, let's have it as greater than or equal to 14. And we'll solve it for y, which will just be subtract 5x, subtract 5x. And we'll have y is greater than or equal to, let's call it negative 5x plus 14. And then I can see that it shades up. And then I can say y equals negative 5x plus 14, and I can create a little table for that. Maybe I'll do that over here. Table of x's and y's. If I were to plug in 0, I'd get 14, so that's sort of convenient. So one of my points is 0, 14. And then if I were to plug in, see if I can be sort of clever here. If I were to plug in 3, I would get negative 1. So 3, negative 1, because negative 5 times 3 is going to be negative 15, and then negative 15 plus 14 is negative 1. So I have all of that information now, so I'm going to get rid of this so I can continue to have room here. And finally, let's worry about equation E. Let's do the same thing there. X plus y is greater than or equal to 9. We could certainly get, well, let me solve it for y. And have y is greater than or equal to negative x plus 9. So it does still shade up. And we could just do x and y intercepts for the points because they're really easy to do. If I need the x-intercept, that's the x value when y is 0, which will be 9. If I want the y-intercept, that's the y value when x is 0. So that also is 9. You should hopefully be able to see that. I was going to do something more with A, but let's graph what we have. Okay. All right. So we got, let's see, for A we've got 0, 0, and 20, 40. So let's say our max is 40. And then it's real easy for me to find 20, right? And I should be able to find most other things at least somewhat easily. So 2040 is up here. So there's A, right? And A is going to shade up. We'll keep that in mind. And actually, we should keep going down here too, because we no longer have the x greater than or equal to 0, y greater than or equal to 0 constraint, so we need to be at least a little bit careful about not confining ourselves to that first quadrant. And then we've got 14, 0. Let's see. 14 is going to be an important number. Let's put it about there. So 14, 0. And 0, 14, that's going to be 20, so we'll put 14 about there. And then there and there. And that one's going to shade down. We'll figure that stuff out a little later. Let's just get all the lines in there first, right? And then y equals 1. Let's have 1 be right there. So that is C. And that one's going to shade up. Okay, so we're starting to see where things are going to happen. And then D was 0, 14 right there. And 3, -1, I should have, maybe I need to do a bigger number for that one. Let's see here. That was -5x plus 14. What happens if I do 4? Boy, I'd really like to do an even bigger number than 4. I'd love to do 14. If I plugged in 14, I'm going to get a really bad negative number, aren't I? 5 times 14 is 50, plus 20 is 70. So -70 plus 14 is 56. So -56. Wow. That's almost as bad. So, well, let's do approximately 3 and approximately -1. Put that 3 in a bad spot. 3 and -1 would be right there. And 0, 14, so it would look, oops, like that, and like that. And then 9009, man, getting really cluttered here. 9009. That doesn't look anything like it, but actually, let me across something like that, right? Something like that. So there's everything, and if I had a bigger, I probably should have done a separate board to make it larger, but there we have it for now. All right, now let's figure out where all the shading goes. So A shades up, B shades down, they wouldn't cross. They should be parallel. Okay. So, let's see. Again, A shades up, B shades down, C shades up, D, which is this one here, and this is E here. D shades up, and E shades down. So, looks like we're going to be shade up, shade down. So between B and E, we're stuck in that little quarter right here between B and E. And then we're above A, above C, and above E. So we wind up in this tiny little area right here. And that's it. That's our whole shaded region. And then the vertices, so I'm not going to go through everything about how to get the vertices, but I will tell you what to do. You isolate, see there's these 4 spots right there. And what you do is, you know, some of those you actually know the whole thing, and some of them you know part of them, but you always know what intersects with what. So, like this one here is the intersection of A and B, so you would make sure that you do a system of A and B and solve that system. Okay, and that's what you do with each one. Wherever they intersect, you set up a system. All right, they're not even going to ask you that in this problem, but I wanted to bring it up and at least talk about it a little bit. All right, so that is our last problem. I'll give you a moment to look at it. And we are done for today. Thank you.